So, warm welcome from my side also. So, I hope you enjoy computer games because the talk is basically about how you can play computer games during your office hours. Because our use case will be demonstrated on some vertical scrolling airplane shooter game. Okay, so what do we do today? I'll give you a gentle introduction to neural networks and a visual explanation about why they work. Then we'll talk a bit about use cases, especially the ones in the front end also. I'll introduce you to TensorFlow in general and TensorFlow.js. Then we'll train a little classifier using a transfer learning approach, and I'll show you how powerful it is and how fast you can train even in your browser. Then we'll use this classifier in a game, the airplane shooter. And then we'll talk a bit about ideas of efficient models nowadays, because previously, let's say in the year 2014, models were still quite slow and you had very powerful hardware to evaluate them, and they didn't work in real time. Okay, so let's start with our little introduction. So basically, there are some types of neural networks. There's the fully connected one, the most basic one. There are convolutional neural networks, which are particularly suited to image or one-dimensional data like voice. And there are LSTMs, and we won't talk about LSTMs today. Okay, how do fully connected networks even work? So there's a theorem in maths which say that a neural network using only one hidden layer can already approximate any continuous function in a compact subspace, in compact subspaces. So how does this work visually? If we have the mild assumption that we're using the S-shaped sigmoid function as an activation, we could say that we weigh our input and add some bias onto it and place it into the sigmoid function. And playing around with the parameters w and b, you can shape this function so that it gets like a step function, that it's very steep instead of being shallow. So we can activate a step, and when we play around a little more with the parameters, we can also see that we can activate the step at a certain position s, just having the parameters minus b divided by w. So we can just model a step that activates at a given position on the x-axis. And if we also weigh the outputs, we can give it a certain height. Because normally the function would go between 0 and 1. Okay, so if we activate a step, we can also deactivate it by just summing those two functions up and weighing the other output by the same factor, let's say minus 8. And so we can model little bumps. And when we can model little bumps, we can sum them up. And when we do this, you can already see that we've got a pretty close approximation to a continuous function here. So that's it visually. And now I want to talk about convolutional neural networks because we will train a classifier on image data today. So how do they work? Let's first of all welcome Lena from OpenCV. We can see here an algorithm that was run on it which detects edges. And filters basically can detect things like edges or frequency content. If you think in terms of like discrete Fourier transformation or Gabor filters, anything like that, you can also extract a frequency information which can recognize patterns. So neural networks will be very powerful because they can process these two kinds of information. So how do filters work in general? Filters have first of all a very limited receptive field. So when you're calculating a value, you look into the neighborhood and you calculate things by multiplying a filter weight by the input, and then you stride this filter along the image. And you get the output values out of it. So you sum it up, add some bias, and you get an output. So a filter also has got a depth. And the filter depth is just the same as the number of input channels. This means if you got an RGB image, you've got 3 input channels, red, green, and blue. And each of the filters will also have a depth of 3. And when we're taking 2 filters, for example, we sum this all up, get one feature map out of it, we take another filter, and we get a second feature map. So you can control how many feature maps you get in the output. And these feature maps may represent some abstract concepts like having detected lines, frequency content, and everything. So that's basically it. You need to multiply and add in general. So how does edge detection work, and why does it work with filters? Basically, when you've got an image, you can say an edge occurs where you've got a change in pixel intensity. Let's say from dark pixels to light pixels. Then at a certain point, you've got a very strong change. So the curve will be very steep at this point. But it's really difficult to process information like this in this curve. But if we take the first derivative, we get some hill-shaped function out of this. And we can say above a certain threshold, we can be confident that we encounter an edge there. And that's what we do. So in classical computer vision, you would use the Sobel operator, which has filters that do discrete differentiation. And there are two components. You want to detect edges horizontally and vertically. And when you add that up, you get an edge detector for basically every edges. OK, so you're not only doing one convolution, but you're stacking convolutions on top of each other, because a neural network is just some nested functions, really. And the low-level features near the input will contain filters that extract the frequency content, gathers the edges, and in the mid layers, you will find more abstract concepts. So when you combine multiple edges, for example, you can make up things like circles. So you see eye-like things here, for example, which are round. And on the right side, you can already see a little bird in there because this model was trained on a data set which also contains birds, people, and everything. OK, but how do we now learn those weights? So there's an optimization algorithm called gradient descent. So you've got a loss function which defines how well your output of your neural network actually fits the desired output. And if it does not fit the desired output well, your loss is very high. And you want to optimize. So in the best case, you've got a convex function where you always find the global minimum. But in general, the landscape is so high-dimensional that you've got a lot of local minima also. And gradient descent says you take the derivative and you descend along this slope of the landscape. OK, this can be difficult, of course. And currently, we are using gradient descent optimizers, but other procedures could be utilized as well. But research is mostly about gradient descent. And there are a lot of modifications because it's so difficult to really get into the right minimum. So on the left side, you can see again, here we can descend into the global minimum. But on the right side, we may end up in this local minimum and not get out of it. But we've got solutions for those ones also. For example, if we're stuck in such a local minimum and we want to get into the next better minimum, we could apply a learning rate schedule. So gradient descent has some step size which defines how much you want to descend. If you've got a too big step size, you just overshoot your minimum. If you're going by slower steps, you will end up in an optimum, but it may be local. So that's why we have a learning rate schedule that looks like this. And we go up again to get out of this minimum and then to converge again into this minimum. So we may end up just in the same optimum, but we may also propel out of it and get into a better minimum. OK, and a really more advanced technique would be stochastic weight averaging. So the basic idea is about ensembles. And when you get into those minima and you get out of them again, you just store them. On the right side, you can see that we've stored 3 minima. And we say our model could get more robust if we just average the weights which we have trained for all those 3 minima. OK, so much about theory. So let's talk about the use cases and get into the real stuff. So in general, you can, of course, do things like fraud detection, time series analysis. You can analyze the weather, stock prices, whatever you can think of. You can do document analysis, and you can also do it in the front end. For example, there are models which might want to extract certain text passages, because if you read an article, it may be long and contain a lot of information, and you would, for example, like to ask a question and get the exact sentence where the question is answered. You could think of solutions like that. There are retrieval tasks. Retrieval means, for example, if you're an artist and you've got a big asset database, you've got a lot of images. But it's difficult to find them again. So your holiday photos already take up a lot of space, and there are a lot of them, I would suggest. And if you want to find a specific one, you want to search, for example, and you could just sketch what you want to have, like a house, and then the neural network could determine similarity between the edges you just drew and the images you've got into your database, and you can retrieve the correct ones. Or you could just convert text to some representation where you can find images also. And then there's also text-to-speech, speech-to-text, and translation. And on translation, I have to say, end of last year was a moment, like the ImageNet moment for text, because models now are so powerful that you can retrain them. Previously, you could not retrain models for natural language processing, for example. And nowadays, there are universal language models, which means that you can apply the same model for a different set of languages, 106 even, with the current BERT model from Google. And you can retrain your tasks, like question answering, just on top of this already pre-trained model, which is great. Okay, but this is more heavyweight. So to be more JavaScript specific, we can, first of all, run things on the client side, or on edge devices, or mobile devices. That also means that data doesn't necessarily have to go from the device to a server. We can just process it locally and adhere to GDPR standards. So we achieve regulatory compliance. And we can also save computational power in the backend, because nowadays, when you run your AI solutions, the backends are pretty heavily utilized. It costs a lot of energy, money, and hardware. So you might want to compute on the client side. And mobile devices, for example, get better and better hardware accelerators. And also, there's a trend that models tend to get smaller and be more powerful. So it's perfectly viable to run things on the client side. You can also save bandwidth. If you need to transfer data to the server, you could, for example, pre-encode an image into a very low-dimensional representation and could just send this representation to the backend to process it further. On mobile devices, this is really great because your bandwidth is limited. And there are alternative control methods, which we'll see in the showcase today. One alternative control method for games could be like gesture control. And you can also build AIs for games. So if you don't want to control your game and go, let's say, out of the webcam image, you could also apply reinforcement learning to play the game further, or you could write AIs that make the bots a bit smarter. Okay, so our current showcase will just be training one classifier that can discriminate between the actions of going left, going right, and doing nothing. And we integrate it into a little browser game which resembles the 1990s Raptor game. Does anyone of you know this game? Great, cool. Okay, so for this we use TensorFlow.js to run it in the browser. TensorFlow initially was developed by Google for internal use for their machine learning use cases. And around 2015 there was an initial release in Python. And there were some C++ parts, especially also for connecting to the graphics device using CUDA. Then they announced the tensor processing units. So they are really integrated into their cloud solutions nowadays, and you can get a lot of power out of them. So your laptop probably can process like 140 gigaflops or 160 using 4 cores. And with tensor processing units, you get 140 teraflops. So that's an order of magnitude higher. Okay, then the first initial release The first stable release came around with GPU, CPU, and TPU support. And they also already announced TensorFlow Lite quite early for Android. So they added just another platform to run on your mobile devices. Then Collaboratory was coming around. It's like a Jupyter notebook. It's like a wiki where you can also code and execute code. And you can make use of the tensor processing units also. And there was the inception of TensorFlow.js to also run it in the browser. And there's also visualization frameworks available for TensorFlow in JavaScript. Okay, and it now really got stable to use. And we've got nearly every platform covered which we want to run models on it. Okay, so about the basic concepts in TensorFlow.js. We're talking about tensors all the time, but what is it? It's just a multidimensional array. Nothing more, nothing less. Operations, like mathematical operations, produce new tensors. And they're really new. You don't modify in place. You're getting an immutable new tensor out of it. And then there are also variables. Variables can be trained, can be learned, for example, like the weights and filters. And you can also have impact on the training process or evaluation process. For example, you could apply advanced techniques like dropout during training, and you don't apply them during test time, for example. And you can control it via variable. And then there's the model, which is just a comprehension of all the functions and takes some inputs and produces outputs, where we can optimize between the input data and the desired outputs. Okay, and one of the most important things in TensorFlow and JavaScript is that you really need to free up memory manually there, because otherwise you're always producing new tensors. They will, for example, end up on your graphics device, and memory does not get freed there, and you get out of memory pretty quickly. So this happened to me a lot when I wrote this thing initially. So I just want to tell you. Okay, and if you don't want to train in the browser, you can, of course, use your Python scripts to train your model on a backend, and you can convert the models and run them in the browser or anywhere else, because you've got a lot of converters for the Android world and everything. Okay, how about hardware acceleration? Actually, hardware acceleration in the browser world is, let's say, better than the backend world, because you're not tied to NVIDIA graphics cards. TensorFlow.js uses WebGL as a backend, and there are shaders. Shaders do a lot of vector and matrix calculations to calculate things like lighting in computer games, and this needs to go pretty fast. And TensorFlow makes use of this. And WebGL is just a standard, which is implemented by all of your graphics vendors, so you're not locked into the NVIDIA world. But if you go into Node.js and run your things in the backend, you can, of course, use CUDA when you've got an NVIDIA graphics device, and this is really faster, but you've got this vendor lock-in. Okay, about development workflow. It's really just simple. You build your model, fit it between the desired outcomes, and then you run your predictions on it. And we'll see how easy this is done in a short example. So on the left side, you see the JavaScript code. And for those of you who have done Keras in Python already, on the right side, you see the Python code. So can you notice any difference? Except for syntax. So it's quite convenient. There's not much difference in there. So in the JavaScript world, we just import our TensorFlow, build a model like a sequential one when we just nest functions. If we need more expressive power, we would use a functional API where we can define functions that can also take multiple inputs, which are important when you are doing approaches like Siamese networks, for example. Then we just add a simple layer in here, just one, which produces an output of one element in this case. And then you call model compile. Model compile takes arguments like the optimizer you want to use and the loss function you're applying to optimize. And then you're defining your data with those tensors here. You give them a shape, and you fit the model between the inputs and outputs using a specified number of epochs. One epoch means you've seen the whole training set once. but we're also dividing things into batches because sometimes not all of the data set can fit into memory, and we don't want to do the gradient update on the whole data set because we would end up in the first local minimum. We don't want that. We're using a more stochastic approach which could circumvent some local minima. Okay, and then when our model is ready, we just call the predict function. So this is a very high-level API, and if you need more control of the training process, you can, of course, use lower-level APIs where you can mess around with the gradients, for example, if you want to clip them at a certain value or whatever you want to do. Okay, let's now train this classifier. First of all, we need to decide on a model architecture. And because we're running in the browser, we need a very efficient one because we want to run our game at more than 24 frames per second. So optimally at 60 frames per second, for example. And a very efficient architecture is the mobile net, and you can get a pre-trained version already from Google. Okay, so how does this work? First of all, you've got an input image of a certain dimension, having your 3 RGB channels. Then this is reduced using some non-standard convolutions, which are more lightweight than the standard convolution I presented earlier. So this uses fewer multiply-add operations and uses fewer space, fewer parameters, and so your model gets faster, more efficient in terms of energy consumption, and so on. And then at a certain point, you want to cut the model because this pre-trained model was trained on ImageNet to recognize 80 classes like people, pizza, and so on. And we don't want a pizza classifier. We want just a classifier which can discriminate between going left, right, and doing nothing. So we cut this in half. Don't take the classification head for the ImageNet data. But we can say that the model already produces nice representations. And because people were already in this training data set, we can transfer this to our domain, which is a bit simpler. Okay, so how do we do this? The most simple case would be to just flatten this volume of 50K values and then put a fully connected model on top of it, which has 3 outputs. And those 3 outputs are our probabilities for going left, right, or doing nothing. Because they are mutually exclusive, we can say that not all 3 probabilities can be 1. So we take a softmax function, which says that the distribution, the cumulative distribution of all of those probabilities equals 1. So no probability can go above 1, and it's mutually exclusive. But 50K values is quite a lot. And on a fully connected network, you've got a weight matrix of, in this case, 50K values times 100 values. And this is really getting quite big. So what do you think? Is the encoder on the left side bigger or the classification head? What do you think? Higher, lower, on par? Any ideas? Yeah, so the classifier is really just as big as the encoder, which we don't want. And there are possible solutions to this. So first of all, when doing classification, we could apply an operation called global average pooling. This global average pooling would condense the 7 times 7 spatial dimension to 1 times 1, and we only keep the depth. This works very well for classification, but we lose spatial information. And for our classifier, spatial information is very important. So in our case, we won't do this. We would just decrease the depth of this volume here, using, for example, a pointwise 1 times 1 convolution, where we can control the number of feature maps that get output. And we could just reduce it to 1 feature map, because basically we only want to know if some person is there or not. So you can really reduce it a lot. And then, again, flatten this volume and put a very, very small dense net on top of it, because we're only having 7 times 7 times 1 values, so around 50 values, multiplied by 100. So this is really smaller. It gets down from 20 megabytes to 20 kilobytes, the model. So this is quite an improvement. Okay, and now I want to show you how powerful this transfer learning technique is actually. So let's capture the 3 actions. I'm going left, and I just capture 2 images. I go right, capture 2 images. And for the center action, I'll also capture 2 images. So when you're thinking about deep learning, you always think you need lots of training data. Yeah, initially, maybe you need a lot of training data to get good representations out of it. But if you can transfer one model to another domain, you can really train using a very limited data set. We'll just invoke training, and on the right side, you see it has already trained, and this was done in the browser. It's already finished. And then we can use it to classify, and let's see if this is action 0. So on the right side, you see the class of 0, you see the class of 1 here, and in the middle, you see the class of 2. So within 2 seconds, it generalized. So that's really great and powerful. And this is also coming to the world of natural language processing using models like BERT. But they are computationally really more heavy than image recognition. But in the computer vision world, models have become quite effective. OK, so how do we code this? Now, we want to get into the real world here, into coding. First of all, we need to gather the data from the webcam. So there's something called device query APIs. And you can say, I want to get user media with certain constraints. And my constraint is the image size, because the model was trained on the fixed size of 224 times 224. So we say we only want video data with this constraint. And when it's available, we just put it onto an HTML5 video element. And you will see it displayed, as you've seen in the GUI previously. And then there's an event loaded data. So when the first frame of data, the first image is available for the webcam, we can start doing other things. So we resolve a promise. This enables us to wait for this process, which might execute asynchronously. And we can wait for it. And after having initialized the video, we can run other code, for example, which depends on this. OK. And from the webcam, we also want to capture data into our data set. And therefore, you find a very convenient method here from pixels. You can put just a video element into it, or just image data, whatever you like, and is an image. And then, because our model initially was pre-trained, it had some pre-processing. And we need to do this pre-processing also to have data of the same scale, of the same value ranges. So what we do here is first expand the first dimension, because TensorFlow expects you to have a batch of data. You're not having one example, but normally you process a lot of examples. So we add this batch access. Convert everything to floats, because RGB data is normally unsigned integer 8. You've got values between 0 and 255. And then we divide by 127 and subtract 1. So you get values that are normalized between -1 and 1. OK, now to the data set. Has some initialization code in it, but the really important thing is the add instance method, where we add one training example to our data set. And here you can see the code that manages memory already. The tidy function will dispose any intermediate tensors that will be created in there. But it will not dispose the result, because you need to work on it furthermore. OK, and now if we want to build our data set, we can only use these operations on immutable data. So we're producing tensors all the time. So in the first case, our data set is empty. So we can just keep this image. We will not dispose it. And we can keep the label we need for this image, which is the class 0, 1, or 2. OK. And then when we've already got one image, we can concatenate it with another one. And we will keep the result, but we will dispose the previous list, because we are creating a new list with one element more. And the previous list needs to be disposed. And that we do using the dispose function. OK, so that's about memory management. Now let's get to the mobile net. From Google Storage APIs, you can download a pre-trained version already. And there's also a parameter, it's called alpha. It reduces the number of feature maps and can also give you back more efficient models using fewer multiply add operations when you decrease this factor to, let's say, 0.75. Okay, but one thing to notice is that TensorFlow can load images from multiple locations. So you can load it from a URL, or you could just load it from the local browser database like IndexedDB. And IndexedDB is really a good place to store large blobs. So we'll use IndexedDB. And we need to define a certain location where we cut this original model because we don't want the image classification. Okay, so when we're loading the truncated model, let's first go into the load model method. So first of all, we decide if we have it locally. When we can load it locally, we just load it from local storage, no internet connection involved. If we cannot, we just download it from our server or from Google directly. Okay, then we've got this model in hand, which is too big and contains this ImageNet classification head. And we want to get rid of this. We want to slice the model somehow. And we can do that by creating a new model, and we say the inputs are just the ones like in the original model, but the output we're giving out is just some output of this mobile net in between the network and not containing the classification head. So we say get layer, and this intermediate layer will be our output. So we slice the model. Okay, and that's basically it about slicing the backbone model to encode the images in the first place. When we want to predict, TensorFlow offers us just a predict function on the model, so this is quite simple. Okay, now for the classification part, we need to train our own classifier here. Our own classifier needs to run data through this backbone model, which we defined earlier, and just uses those values, which are of a lower dimensionality, to run them through our little classification head. Okay, so we will just do that. When creating our classification head, we've got some choices. Like we could produce a small model using some pointwise convolution. Pointwise means we have a kernel size of 1 times 1. And we only need one filter to have one feature map output because I'm only interested in people here. Okay, then we flatten this. And on top of it, we would apply this dense classification head. Or if we want to go by the bigger model, which really needs only a low set of examples, we could just flatten it directly and run it through the classifier. Okay, then we put this list of layers into a sequential model and return it. And when we do predictions or classifications, we will run the data first through our backbone model, get those embeddings out of it, and put those embeddings into our own model and get the output out of it. When we want to have a class, we also need to apply some transformation because we will get 3 probabilities out of it for going left, right, or doing nothing. But in the end, we're interested in one class that says left, right, nothing, like 0, 1, 2. And there's an encoding called, so basically this is in one hot encoding, having 3 probabilities. And we want to get the maximum probability because there we're most confident that this action should apply. So let's say when I'm going left, the probability of going left is like 0.7, and the other probabilities are lower. I want to take this highest probability, and this is done using the argmax function. And the argmax returns us the index where the highest probability was. And the index could then be 0, 1, or 2 for our actions. Okay. Saving the model, by the way, is as easy as loading it, just calling the save method, and you put your URL into it, like IndexedDB :/ something. And loading is just as easy as well, using the load model function. In this case, we could load the model from an HTML file input, for example. Okay, then we've got our whole model. We've got the backbone, we've got the classification head now, and now we need to fit it to our data. How do we do that? We just write a little train function, instantiate one optimizer. Adam is a very advanced one. It does best effort. And I think it also uses second derivatives because there are some kind of saddle points and so on in your landscape, in your optimization landscape. And it makes use of that as well, if I'm informed correctly. And then we just get our model as we defined it and compile it using the optimizer, and we specify a loss function. The loss function in this case would be softmax categorical entropy because we want those probabilities not to be higher than 1, mutually exclusive, and cross entropy is great for categorical data. If you would regress, you take something like mean squared error, for example. Okay, and then we call the fit method. And into this fit method, we can also provide some callbacks to it, because some strange things might happen from time to time. Let's suppose you had a logarithmic operation in there. If you want to search for the logarithm of 0, you will search for a long time because it is non-existent. You will get not a value out of it. And when you calculate something with not a value, basically everything else will get not a value in the end, and your whole model will be dead. So there is a callback, for example, that terminates training on not a number values. But in fact, when you're using the cross-entropy function here, there's a little trick they apply. So because values are between 0 and 1, and the only thing that can happen is that you get a 0 into this logarithm, and you can prevent this by just adding a little epsilon. You don't make it too big because you're shifting values away and you cannot train anymore. You're just using a very, very small value epsilon so that it's not 0 anymore. And so you could avoid bad things. Also, when you specify a lot of epochs because you don't know how long your training will take, let's say you specify 1,000 epochs, it could take forever, and the model will tend to overfit. So it will learn the training data by heart, but it will not generalize on the validation data because it's only learning by heart and not generalizing anymore. And we can also prevent that. There's an early stopping callback. You would utilize this and say, if my validation score does not increase for 5 epochs, I will stop training. So you can say, if it's necessary, train for 1,000 epochs. But if you're already trained, please finish training. And there's also a callback that saves the best model. Okay, so much about training. Now we want to use it in our game. So the code for this is like you instantiate your webcam again to gather the webcam data, initialize it, load your backbone model from some URL. You have stored it on your server probably. And models are represented using 2 files. There's one JSON file which specifies the model architecture and where you find the weights. And there's this binary weight file, which when you're taking float 32s, is just a file that contains consecutive 32-bit floating point values. And therefore, you will use, or TensorFlow will use the architectural information to put those weights into the correct convolutional filters. Okay, and then we also slice our model and put it into the classifier. And then our gesture input is initialized. Then when we want to write a handler, we can use an endless function. But it's not bad to have endless functions because we can do it asynchronously, indicated by async here. So it won't get into our way, and we can also do other computations at nearly the same time, because at some point in time, we will wait on the next animation frame, and when we do that, other code can be executed. And when this code has executed, our loop will continue. Okay, so here again, we don't want to get out of memory. We use the tftidy function for memory management, put our input image gathered from the webcam through our encoder model. We get the embeddings out of it. We run those embeddings through our classifier, and then get back the data, because it might be stored in graphics memory when you use WebGL acceleration. So, and then you get your class out of it, because the classification method already uses the argmax here. And if it's class 0, we would move left in our game. If it's class 1, we would move right, or we could just stop moving. Okay, so that's basically it. And now I want to present you with the current version of the game, where you can actually do much more than going just left and right. You can also switch weapons. You can go to the most powerful weapon. You can stop shooting at all, because energy and rockets might be limited. And we're really regressing on the spatial dimension here. So what I'm doing here is not using a classification model anymore. I'm using a postnet here, which does regression. But beware, regression models are much harder to train, because neural networks have so many parameters. it's really hard to get each of those parameters right. If you only see data here and there, in between, the model could just do weird things. So to get a stable regression without outliers and noise in it is really hard, and you need a lot more training data for this. But you can also improve your use case here. Okay, so what about efficient models? There are two types of model families I want to present. So there are dense nets. Please don't confuse them with a fully connected network. Dense nets are convolutional. And there are mobile nets, which are also very parameter efficient. And when you're using mobile nets, you can benefit from big companies because you've got pre-trained models for doing things like object detection. There's an SSD Lite based on mobile net. SSD, it's called single-shot multibox detector. It only does a single pass over the image, but it can give you a lot of bounding boxes for a lot of different classes. So you could run it on an image, and you can, if you've got a smart fridge at home, for example, you could have classified all your vegetables in just one inference pass. Okay, there's also DeepLab for segmentation. Segmentation means that you want to have a mask where things really are. So if you want to do anonymization, for example, you would need to have a person mask to just blur it out, for example. You can use DeepLab. DeepLab has only 2.11 million parameters. So that's not so many. And then there's the PostNet for the post estimation. And for the mobile use case, it uses a bottom-up approach. This means that it just filters and produces a heat map out of it where you could locate key points like the wrist joint or the nose or the eyes. And this heat map, of course, you need to decide on where your actual key point really is. And it's normally the one with the highest confidence. And you suppress all the probabilities around it because they are also quite high, but not the highest in this radius. This is called non-maximum suppression. And of course, there's also another approach. This approach works really well, it's fast, but if you really need high accuracy, normally you take two-stage detectors. A two-stage detector would first of all determine regions of interest, like rectangles, where you could find potentially interesting things. And then you're cropping these regions of interest, and you're running a segmentation model on each of those cropped regions, and you suppress the things with the background classes, which you're not interested in. Okay, so modern convolutional networks build upon some ideas. One of them are bottleneck structures. Bottleneck means when you've got this width times height times depth volume, you could decrease it in depth because normally you get some feature map out of an operation, but it is possible to compress this representation, and it's also powerful. And we do this compression, and we get a lot fewer feature maps out of it. And when we do further processing, we process it on fewer feature maps, which gives us a great speed up. And then there's also the concept of shortcuts and feature reuse. So on the left side, we see a ResNet block. ResNets have been quite popular for a long time, and they're still popular and used in some model architectures. And the basic idea is that when you make a model very deep, you can get problems like vanishing gradient. So if you imagine the S-shaped sigmoid function, when you use it, and you take the derivative at the ends, the derivative is nearly zero. Yeah? Here the derivative is quite high, but in the end, it's not high. And when you're nesting functions, you need to apply the Leibniz chain rule. And this means you need to multiply. And multiplying small values with small values gives you a diminishing signal. So you might not update weights anymore because your signal diminishes. And therefore, they introduce some shortcut function, which is just the identity function. And during backprop, you could just take this shortcut to calculate weight updates here. And they also add this to the output of the layer in between, because they say, if the previous layer already produces useful information, you wouldn't have to learn anything in here. So when the model is too deep and you're using regularization, which penalizes weights a bit, all those weights would be pushed to 0. And this would not introduce noise anymore. So you can make your model arbitrarily deep without losing accuracy. This is the idea of ResNets. Another model which I find very interesting are the dense nets. Dense nets do not add things, but they concatenate feature maps. And by this concatenation of feature maps between the convolutions, you also get a connection between the output and the operation on the input to propagate your signal when doing the gradient descent. So basically, you will avoid vanishing gradient problems with this as well. And in between the layers, you only use a fixed growth rate. So when you're writing a very simple convolutional model, you're going from 64 to 128 to 256 filters. And this gets computationally heavy. But in here, we only grow by a fixed rate, let's say 16 filters, because the model has the property, because it concatenates, it has the property that it can preserve information that was already learned. So you've got this property, and you also learn new things by this fixed set of filters. And when you think of neural networks not in the form of representation learning, but in the form of a program that gets executed, you can imagine you may want to calculate one value, and you want to do 2 different calculations on top of it. And so this is the idea behind the dense net. Okay, and then there are also non-standard convolutions. So in the beginning, we've seen the normal convolution. In here, let's denote M as the number of input filters and N as the number of the depth of the feature map we get out of it. And in this example, we will go from 16 to 32 in depth, and we'll use a kernel size of 3 times 3. When we do a standard convolution, we just have M times N times kernel size. And this is like 4,608 parameters in here. But if we would separate this operation, like in the Sobel filter, if we separate it into one spatial convolution and one pointwise convolution, then we can get along with fewer parameters and fewer multiply-add operations. So when we do this, first of all, we only have as many filters as input channels. So we've got M times kernel size times kernel size. This is 144 parameters. And then we do the pointwise convolutions, and we have as many filters as we want to have output depth. And we've got 1 times 1 times output depth for a single filter times N. Those are the 512 parameters on this side. And you're getting to 656. So this is really only 7% of the parameters of the standard convolution. And also, you're using fewer multiply-add operations, and so your network gets more efficient. Okay, so let's sum the improvement a bit up. In 2014, the VGG60 model had around 140 million parameters, and now some segmentation model, which can produce pixel masks already, has only 2.1 million parameters. I would say this is a great improvement. So if you want, if you want to check if I told you something wrong, you may correct me, you may write me an email, and you can use those sources for this. Okay, time for questions.
Yeah, thanks a lot for this interesting talk. Are there any quick questions?
Yes, please.
So you were mentioning that TensorFlow.js uses WebGL.
Mm-hmm.
That's very reminiscent of the days when you were using graphics cards to, like, when you want to do computations, to write shaders. But now we have compute shaders, right? So browsers don't support this. Do you have any idea if TensorFlow.js is going to stick with WebGL, or is there something? I mean, can you run this faster in Rust or something like this?
I think first of all, TensorFlow.js is, let's say, very new. Mm-hmm. So it just got stable this year. And the first decision of them was to use WebGL, so I think they won't get away from it so soon, because it's a lot of development work. But in the end, you could file an issue in their Git repository And you could say, hey, you can use other techniques as well, because they are already using backends. So you can calculate it on the CPU or using WebGL if you've got it available. So it's possible to use different backends, but it's not implemented yet.
Okay, thanks.
One more question, maybe?
What is the preferred database when you handle tensors in connection with AI?
The preferred database. So for your pre-processing input data and so on, I would say in most of the cases you get away with flat files, and you want to store data in a way you can read it sequentially. So you won't use relational databases because the memory access pattern is quite spread along the memory, and you just normally take flat files where you can consecutively read things in a fast way. Okay.
We have time for one very last question, if there is. Well, in the meanwhile,
okay.
I will thank our speaker again.
Yeah, thank you.
So.
Yeah.